Hello, I'm Pen Lin from Sun Yat-sen University. I will talk about our work, multi-instance reference image segmentation of sense gauges based on global reference mechanism. I will talk about the background and the motivation. Sense gauge segmentation based on reference expression plays an important role in gauge editing of animal industry. For example, for input sense gauge and input text like the house is pink, we need to construct a model to code the sense gauge automatically. The majority of reference image segmentation work with natural images, and very few focus on sketches that have unique characteristics. For example, when the input image is A and the expression is the two sheep on the left of the car, most methods are tailored for binary mask generation with only one output mask covering a single target instance or a group of objects like B. Next, I will introduce some related works. MATDNet is a text-based single-instance object segmentation model. It proposes the subject module, location module, and the relationship module. In each module, they use the attention magnet to compute the matching score between text and the ROI region. They cannot handle multi-instance object segmentation problem, and the relationship module is modeled based on distance and can only handle local information. Sketch colorization proposes a text-based two-stage framework for multi-instance segmentation of sense gauges. The pipeline includes two stages. In stage 1, segment out the region of the input image corresponding to the input text as a binary mask. In stage 2, in order to get multi-instance masks, they use a pre-trained instance segmentation model like mask RCM to get our instance masks, and then matching the area of the binary mask with our instance masks to obtain the final target instance masks. Obviously, the two stages cannot be optimized synchronously, and problem in either stage will lead to poor overall performance. MDTR is a text-based two-stage multi-instance segmentation model for natural images. It also includes two stages. In stage 1, fine-tune the training model to enable the model to complete text-based multi-instance target detection compatibilities. In stage 2, fix the target detection model parameters, edit segmentation head for separate training to finish the multi-instance reference segmentation task. MDTR highly dependent on pre-training process. The two stages are basically independent, and the later stage is very dependent on the performance of the former stage, which is easy to cause error accumulation. Next, I will introduce our method. We propose a one-stage framework GIMNet for multi-instance reference image segmentation of sense gauges with a two-step language fusion in a cost-to-find manner. The framework consists of three parts: A. Segmentation model, B. Language model, and C. Global reference mechanism. We might describe the global reference mechanism. The other detailed information of our framework, please look at our main paper. The key idea of the global reference mechanism is to assign references to each ROI in global manner. For example, when the candidate is a rightmost tree, grid dotted triangle, it can get the reference information from all trees or other traces under the house. As long as the consistency score is high, no matter how far it is from the candidate, it can provide reference information. This is the meaning of globe. With the global reference mechanism, the performance of our model can be greatly improved. Next, I will show some results. From Table 1, we can see that the conventional methods designed for the standard task perform poorly. This is because when applied to the examples with multi-targets, they output a unified mask for all targets, which tends to lead to poor instance segmentation measurement, like AP. The above image is the visualization results, showing the poor performance too. As for the comparison with the only approach closest to our framework, namely Zoe, ours outperforms by a large margin. From the quantitative results as shown above, we can see that Zoe fails in some cases where the expression specifies what the instances of the same category, like A, in some cases where single target specified, like B, it tends to output undesired instances. Moreover, when it is able to locate the correct instances, some segmentation masks are not able to cover the whole object completely, like C. In contrast, our model works better on these cases and produces visually more complete masks. The quantitative and qualitative results both imply that our one-stage framework is more effective because of the joint training in an end-to-end manner. Besides, we do the evaluation study of configurations of the global reference mechanism. Quantitative results in Table 3 show that the distance-based selection manner works worse than our consistency-based approach, probably due to its lack of ability in accessing necessary reference far away. Incorporating the absolute positional information brings slight improvement, but locking reference information from the GRM has further improvement. When employing GRM with k equals 10, the performance improves by a large margin, but the model suffers performance degradation when k equals 5 or 20. Our model with 5-dimensional reference information superior to the model with 3-dimensional one. We show how the proposed global reference mechanism works by visualizing the intermediate results as shown above. After the rough factoring in the appearance stage, like B and D, model with or without GRM has positive proposals covering the correct and incorrect instances. Without the GRM, like C, the model predicts the positive proposals after the appearance stage as object class instances, leading to incorrectly identified outputs. With the reference assignment and the global view offered by the GRM, like E, the model learns to classify the incorrectly identified proposals as non-object which have a low probability of being their real object class. Hence, these non-object instances that are mismatched with the expression are removed from the final outputs. Next, I will talk about the limitations of our approach. First, since we use the training and the test states in the sketchy scenes matching dataset, where textual expressions are created automatically based on templates. Therefore, some of these seem unnatural and may contain grammar mistakes. Secondly, in our GRM module, we employ a simple process of information combination, and thus the framework tends to fail on some complicated cases. With numerous instances, graphic neural networks can be adopted in the GRM model to strengthen reference information. At last, I will have a conclusion of my representation. We present a one-stage framework for multi-instance reference image segmentation of set sketches, which is demonstrated through our experiments to be superior to the two-stage approaches with the pre-training process. Our proposed global reference mechanism provides a global view for the model to identify the position of each detected candidate in order to improve the segmentation accuracy. Finally, we also show how the GRM works by visualizing the intermediate results. Thank you.